Hi, welcome to the Signal Path. In this episode, I'm going to do a follow-up on the repair of this Agilent power supply that I started a while ago. And if you remember, I couldn't completely finish the repair because I didn't have the correct microprocessor here with the mask ROM version that was appropriate to this display. And I posted this online, of course, and there was a lot of people discussing various things that I could do, and some of the suggestions involved actually decapping the IC, finding out what the code was written in there and write it to a flash version of that IC. And that is possible because the mask ROM can be read optically, essentially, because this is nothing more than metallization connections in the back end of line of that particular IC. So you could actually potentially do that. That's a lot of work and a lot of hassle, and I didn't have time to do that. But it happens that a gentleman by the name of Gerry Sweeney kindly contacted me and told me that he had one of these broken panels, but his panel was completely broken, so I couldn't reuse it. But he could take off the microprocessor and send it to me, and he sent it to me all the way from his country. And interesting enough, I was actually already subscribed to Gerry's YouTube channel. He has a really nice YouTube channel where he's done a lot of different teardowns of repairs and upgrades of different Agilent and Keysight equipment, and he speaks very well and describes things really well. And I was already watching his videos before he even had contacted me, so I have put a link to his channel and to his website in the description of this video, and also on my website. Please give him a shot from me and tell him that I said thank you as well. I've already sent my regards as well. And so anyhow, this arrived, and there's only a single IC here, and we're going to take a look at it. This, of course, in an anti-static bag, but I'm not gonna stop there. Hopefully this will repair it and this will come back to life, and that's great. But I was interested in actually going ahead and trying to decap some of the broken ICs that I took off of the old board. So the VFD controller, which I described as being potentially the possible cause of the failure, and this is the microprocessor that was already on this board, and this is another one that I bought at a time not realizing the mask ROM problem that this had. And I'm curious to see, well, what's in here also. Now if we decap these, we can actually see the damage done to the silicon, which might itself be quite interesting, and then we can also take a look at this. So this video is not just going to be me finishing this. That would kind of be boring. Hopefully it will come back to life, and that would be great. But other than that, I'm going to try and decap this. So there's going to be a lot of interesting learning experience from this, and we'll look at it under the microscope. So don't just stop watching once I replace this. So I'm going to go ahead, just take this out, put it on, over here, and solder it back down, plug it in, see if it powers on, and we'll close it up. I don't think it's necessary for me to show you me soldering this back. That's probably the boring part. I'm also really excited to get to the decapping process. So let me go ahead and solder this on here and see what happens. Alright, so I put the IC in there, and I soldered back down that metallic shield that used to be around it, where I had to actually cut the pins out. If you watch the old video, anyhow, there's a piece of tape on there just to hold the VFD in place. I probably have to glue it because I've bent it forward, so now there is its rest position is not flat anymore because I cannot bend it beyond this angle, so it kind of sticks out. So I think it will line itself up once I put it into the plastic exposure. But check this out. Look at this. Power it on, and voila, look at that. It actually works. The display works. The instrument passes that self-testing that it does initially, and now it says output off. And I'm not going to touch it because it has high voltage on it, not because of safety, but because the high voltages are actually on the grid, and I don't want to damage the microprocessor by putting a very high voltage through the high impedance nodes, especially on the button. So I'm going to be careful with that. But let's go ahead and put it into the plastic module and take it from there. Here we are. I put it all back together just to save some time. I actually have two of these, and now they are both fully functional. There we go. And they of course both work perfectly well, and I can adjust the voltage on both of them. Sorry, they're sideways. I don't have any more room in the lab here right now, but everything works perfectly. And we saw that I actually did test the output voltage and current of this unit before. It's actually this one, the new one, the one that I just fixed, and it works perfectly fine. It wasn't that the actual power supply was bad, it was just a display module. So after a whole bunch of waiting and back and forth and so on, finally got it to work nice and beautiful. So now let's turn our attention to something else. So before we get to the IC decapping, I had totally forgotten about this other power supply, which I said I would repair during the last video when I was trying to repair the other Agilent, the E36 E3642A, and this one is a E3620A. This is a dual power supply, dual isolated, from 0 to 25 volts and 0 to 1 amps. It doesn't actually have current adjustable current limiting. It will limit all the way to 1 amp, and it has 2 channels which you can select between them, and this also is a broken unit. I've plugged it in, and if you go ahead and turn it on, you can see the display comes on and it says minus 0.54 volts and you know, some small amount of current, and I switch to the other channel and it just says 0. And interestingly enough, you know, if I adjust this all the way, which should take it to 25 volts, it doesn't do anything basically. And same to the other one. This just basically shows 0. Now, I don't know what's wrong with it, but one thing we should start doing is maybe just look at the output voltage and find out what's wrong. And it could be that the display ATD converter and the display that monitors the voltages is actually broken. That's one possibility. Or the problem could be internally. I have no idea. But let's go ahead and plug it into a multimeter. That should be a good starting point. Here we go. I'll plug in. Power this on. Ah, that's interesting. Look at that. It actually says minus 0.5374. So it does match the voltage that used to be there. And if I increase it, yep, you can see this increases a little bit just like that. So the display is in fact reading the correct voltage that's on the terminal. So that's interesting. And if I go to the other channel, and if I go and measure the other channel voltage, let's see. If I do go ahead here, yeah, that one is reading about 40 millivolt. This is reading about 5 millivolts or so. So yeah, no, it's wrong. It doesn't match. It's completely off. There's no output basically. So something else is wrong. Well, that's okay. We want to take it apart and see what it looks like. So taking these units apart is actually fairly straightforward because it has these little latches. I just put a screwdriver on there and turned it. So let me take it off from the power here, and I should be able to, I think. There we go. Oh, it's squeaking. There we go. Let's see. Whoa. If I can get this thing off. There it is. Nice and easy. Ooh, looks nice on the inside. And I don't know if you've ever seen the inside of one of these. Of course, the main transformer is the first thing you see. And here's the main line voltage going from the plug directly onto the PCB. I don't like the fact that it has no shrink tube here. Like, this is live. I mean, sitting there. Anyhow, that's not very impressed by that. But oh, actually, whoa! Look at that. Check this out. And you must have seen it already. What has happened here? It's like an explosion. There's like a war zone in here. And you know, looking at it, I don't know if it shows up on camera, but this doesn't actually look like that it's the IEC that has failed. It almost looks like something water damage. Oh, there's even more of it here. There we go. You can see some more here. The shadow might be preventing you from seeing it there, but there it is. It's much more clear like this. Yeah, it has some major damage to it. And I wonder how this has happened. This component here, I can recognize. That's obviously a rectifier right there, a 4-diode rectifier, like a bridge. And on this side, let me flip this over so we can get a better look at this guy here. Yeah, and the part number on that is an LM339, it says, I think, which is might be a comparator, set of comparators perhaps. But yeah, that's pretty bad. So obviously, I don't know what else could be wrong with it, but naturally, the very first thing we should try to do is to completely open it up and see what is actually going on the other side of the board, if the damage extends to that side. But certainly here we have some major problem, and we have to start replacing those components. There's even some here, some kind of a rusty material. Now maybe water has gone into it, but I don't quite know how that would be, because the way this was, it was like this. So underneath here there are no holes here. So, oh no, wait a second, no, I take that back. It was like this. Ah, that might explain it. So there's actually an opening here, so if something pours in, it will go directly onto the board. Yeah, I remember this 115 volt is of course right next to the plug. That's how it was. There we go. So that explains it. Some water must have come inside. Of course, there is no reminiscence of it left. Okay, there you go. Well, that is a partial explanation of what is going on. So let's disassemble this further, take a closer look there, write down the part numbers, see if I have any of those in my bins, start replacing them and see if it comes back to life. That would be a really, really easy repair. I mean, this is basically as straightforward as it can get. But nonetheless, it's interesting to take a look inside it and maybe see if I can find the schematic. We'll see how it works. There it is, taken out of the case, and interestingly enough, the back of the board looks pretty good. So the damage, whatever it was, it's very heavy, is only at the top surface, and all the more reason to believe that this has had some kind of a liquid poured into it by mistake, because you can clearly see here some leftover residue of whatever liquid that has gone through where this hole used to be, and this pin here actually goes through the board and latches onto the board. Where is it? It's somewhere here in the center, close to here. There it is. That hole right there. I don't know if you can see. You can see the back of it, my hand right there. That one right there is where that pin goes through. And of course, if there is any liquid in there, then the only way for it to be able to reach here, and only reach here, is if it has gone through from around the edges of that hole. So I'm pretty convinced that this has some water damage, and hopefully that the failures from the components that have directly received the water damage are limited only to those components. That, of course, there's no way to be sure, but we can go from there. Oh, I'm clicking this thing back and forth here, and the display here looks like it has the A to D converter built into it, so I think at least. So therefore, if it's showing the correct voltages, it means that the board is probably okay. I can't disconnect it completely because it has some stuff that are soldered, and the main jacks do not come off, I don't think. So I'm gonna have to keep it together like this. By the way, this also has a switch to select the voltages, so this is compatible. You know, it does say 115 volts only because it's hardware set to 115, but you could potentially run this anywhere in the world. So let's go ahead. Again, I'm not going to go through the boring soldering, especially because these are through hole. I'll clean them, take them out, and I will take a look at what components those actually are and see if I have any replacement. I'll do a general cleaning, and then we'll go from there. So I removed these components, but the damage is quite extensive, and he has basically destroyed all the pads, and it's very difficult to get this out while it was also rusted. Let me see if I can get this to focus. So unfortunately, as a result of that, there's been quite a bit of damage to the board, so it'll have to be repaired. But first thing is to clean it completely. I took out the three components that I felt were the ones that were most damaged. So here you can see actually the pins of this just pulled right out of it. This is obviously a bridge rectifier. There's a capacitor here as well that is damaged. So I'm going to go ahead and clean the board. Now the way I'm going to do the cleaning is basically I'm going to put alcohol on it, and I'm going to use a toothbrush. I'm going to work, you know, gently over everything and then dry it out completely, and I'll bring the board back and then show you what it looks like after cleaning. Hopefully it'll look much better, and then we'll see what the damage to the traces are, and we can go ahead and replace it. I'll find out what component it was. I actually haven't looked at it yet. It's an LM339, I think. Let me see. If we can zoom in here. What does it say? It's upside down. Yeah, it's an LM339. I'll check to see what it is. Either quad op amp or quad comparator, I can't remember. But anyhow, let's go ahead and see what happens then. So here's a clean view of where that component used to be. You can see several of the traces have come off. Here's one of them, for example, and here's the other one that used to connect to those various pins. So it will have to be surgically corrected in a way, because otherwise obviously those pins will not make contact. So I'm gonna keep track of what's going on here so that it can be done and it can be corrected once the component is installed. And same for this guy right here. You can see that the pins have to be very, very carefully placed back to make contact. Now this is even harder because I have no clear access to that point, unfortunately, so I'll have to find a way to connect it up. Well, here's some micro work that I've done here. I guess can't really call it micro work, but some small corrections. I've put some cables here. I think there might be too much reflection on this for you to see it. There we go. So wherever there was a trace that was broken, I put a wire through that pin, and I intend to basically use a socket in its place to be able to push through those pins and go to the other side and basically make connection to the traces on the top. And I took a picture of this before, so that I can double check the connections, because this board is only 2 layers, so it should make it fairly simple. So I'm going to go ahead and install this and do a little quick check with a multimeter before we move to the other one. The rectifier bridge is going to be much more difficult because there's very little room to work there. So let's go one step at a time. Alright, here's our socket in place, and here is, whoa, that's way too close, and here's the picture that I took. So now I can use this this photograph and find out if all my connections are there, and in fact I just quickly did that, and yes, all the connections that were supposed to be made to all the traces up here, for example all these broken ones, you can see this one was broken, this one was broken, and they're all making contact. So at least this seems to be good. So I can now put in a replacement IC in there and turn my attention to the other really badly damaged PCB trace up there. So for this part I'm going to try to use the Dremel, and I'm going to see if I can remove the solder mask directly from the board and expose the copper, and that would allow me to solder some cables to that copper. It's very difficult to reach with it and scrape it off with something like a knife. So if I can expose enough of the metal there, then I can solder 2 vertical wires to it and just bring the whole thing out and solder it kind of a little bit maybe higher than where it's supposed to be sitting initially, or just bend the pins and lay them on top of the traces and solder them that way, depending on how much of it I can clear out. I also checked the capacitor. It actually is fine. It was just very dirty. I measured this value and everything's okay, so I can put the capacitor back where it was. The traces for that are okay. So this is going to take a bit of work to get the traces cleaned up, but let me see what I can do. Here we go. That's not too bad. It's really hard to hold this. I apologize. There we go. So you can see I took away the solder mask there. You can clearly see the damage that was done to the pins. So now I have exposed copper, and that's going to make it a lot easier to solder this thing back down. And also what I've done is that I have bent the legs, here we go, of my rectifier. So if I were to place it back, sorry if my hand is blocking it, just give it a second. There it is. It's going to rest like that. Look at that, it lines up so beautifully. Now all I need to do is to apply the solder to that area, and it's going to flood it and make a nice connection to those copper wires, and then I'm going to put the capacitor in afterwards to give me some more room than before I put the cap in, and the cap gets soldered to the other side anyway, and then it should be all nice and great. And there is no guarantee that it's going to come back to life. I put the LM339 there. By the way, that was a quad competitor that was there, and it doesn't mean it's going to come back to life, because this damage could have killed something else, but there's only one way to find out. Alright, I was just about to power this on. You can see that I have installed everything in, but I happened to look around very carefully, and look what I discovered. You see that? Oh, let me see if it will focus. That point is actually not connected. This is a break in the circuit, so this wire here isn't connected to these 2 wires. And I was just looking at it under a magnifying glass, and I noticed, and this, a problem like this would be so difficult to find, and that is a damage caused by the rusting of the traces due to whatever that happened, whatever that spilled into it. But I think everything else is okay, so let's go ahead and I'm gonna go ahead and fix this, and we'll power it on. Alright, here's the fixed open circuit, and believe it or not, I held it under the light and I found another open. This thing is just a disaster. So this trace here that you can see right here that goes into this via actually doesn't connect to this via. There's a break in the circuit, and I couldn't fix it on this layer anymore. So what I did was that I went to the back of the circuit. Let me see if I can flip this up, and I added a little jumper wire, this red wire here, to basically jump that gap and clear that open. It's just crazy. I went again, I looked at it very carefully this time. I hope there are no more opens, because I really want to power it on and test it, but it's to be expected in this area. I'd have to do a pretty close inspection, because this is where all the rust had happened and all the traces had been exposed to long-term moisture or something. But it looks okay, and everything else seems good so far, and let's see, let's plug it in finally. Alright, all plugged in. Let me turn this on without touching anything. There we go. Oh, it says 0. What's going on here? What do I have selected here? Let me see. There you go. Now I have selected voltage 1. 0. Let's see. Look at that. It works. There you go. It should go all the way to 25 or so. There you go. 27.8. What about the other channel? Let me switch to the other channel. There you go. Yes, that's what I'm talking about. All the way to 27. Beautiful. So both of the channels are now alive, and I think they have output, but before I check the outputs, I'm going to put it back in its case and just clean up a little bit more. But this looks good. It looks like it's back to life. This is fantastic. There you go. Save another equipment from ending up in the garbage. This is good. Fantastic. Alright, so looks good. Here we go. We can go to let's say 5 volts here on channel 1. As close as I can get it to 5. There you go. Oh, come on. 5.00. There it is. There you can see it's almost it's very difficult with this thing to actually get it to be exactly a certain number. Here's 5 volts. There it is, and you can see it's 5.00, and this says 5.00. So it's working pretty well and looks to be in fairly good calibration status as well. Let's go here up to 5 volts as well. There you go, 5.00, and this guy is also saying 5.00, 5.01. So it's pretty close to what it should be. I can also try out the current, since this thing will max out at 1 amp anyway. I can easily go ahead here and put this on the amp and plug it into here, and 1.058, and this is saying exactly 1.058. so it looks good. And the other channel, just for completeness as well, 1.0571, 1.055. so looks good, and I think it's in actually pretty good calibration status as well. The only thing that is wrong with it still is that it's missing the buttons. They are broken. These are notorious to break on these models of the Agilent ones, and I think you can buy them, but I don't know where to. If you know where I can get some of these easily, except from Agilent's website, let me know. But there it is. So I'm eager to get to the IC decapping. Let's go. Now that we've taken care of the power supplies, we can turn our attention to try and decap these ICs. Now this process refers to essentially removing the epoxy inside these packages so that we can expose the silicon inside, and we can see the silicon with the wire bonds going around to the different pins. Now that process can be done in many different ways, but I want to do it in a way which doesn't damage the IC, so we can take a look at it under the microscope. People try to grind them and break them and so on, but of course that always runs the risk of damaging the IC that's inside it. So the other way people try to do this is by essentially dissolving it chemically, and they often use nitric acid. Now HNO3 nitric acid comes in different concentrations, of course, and the very high concentration versions of it, above 86%, are called fuming nitric acid, and if at very high concentration, it would be red fuming nitric acid. And at those levels of concentration, the fluid is actually yellow because it has nitrogen dioxide as a contaminant in it, and it's extremely dangerous. Nitrogen dioxide is poisonous to breathe, of course, and nitric acid is highly corrosive, is an oxidizer, and it's the only acid that I know that can actually react with copper, and that reaction itself will create nitrogen dioxide, which is poisonous to breathe. It's a brownish colored gas that comes off the surface of the liquid. I used to work in a chemistry lab, and I actually am certified to use high concentrations of dangerous chemicals as well as operating high power lasers, but you have to be extremely careful because you have to have goggles, and you have to make sure that you're wearing protective gear and you have gloves on and everything, because it only takes one splash of this liquid into your eye to forever change your life. It's not worth taking any risk at all. So one of the things I'm going to do is I'm going to remove all the pins from these packages because they contain copper, of course, and I don't want the copper to react with nitric acid, not just because of the poisonous gas, but also because I don't want to reduce the concentration of the acid and use some of that to react with the copper inside the lid. So I'm going to cut all the lids off and I'm going to sand them all off to reduce the metal contaminant in this process as much as possible. The other issue is that the reaction is very slow at room temperature, which means it has to be heated up in order to speed up the reaction and dissolve the epoxy, making the whole thing even more dangerous because now you have essentially boiling acid, so even far more dangerous than before. So it has to be done outside, it has to be done under a fume hood, and it has to be done with all the protective gear you can think of. And do not try this unless you have some experience with this. And just, if your enthusiasm is curbed enough by just seeing it on video, be content with that. Do not try to put yourself in danger. But anyhow, either way, let's go ahead and try and see if we can do this and see if we can get some silicon out and look at it under the microscope. There we go. This is as good as we're gonna get. Of course, the pins are still they're completely smooth. They're now inside the package, and surely that's going to react with the acid, and you're going to be able to see the green and the brown reaction that nitric acid has with copper. Now, there's other. I haven't decided which way I'm going to do this. Whether I'm going to put these into the acid first and then turn the heater on, or I'm going to first heat these and then apply a small amount of acid to them. But I think I'm just going to try just a straightforward method. Put them into the acid at room temperature, then place the acid on the heater and carefully raise the temperature until we get a more violent reaction, and see if we can dissolve all the package. There's a lot of epoxy here, so I hope I actually have enough acid to react both with the copper and get rid of the epoxy. So there's only one way to find out. Alright, here we are outside. Here's the three ICs here. This is a Pyrex container, of course, which is has to be because we're going to be heated up, so be very careful. You can't just do this in any container. And I'm going to go ahead and add some acid to this and then turn the heat on and see what happens. Here we go. You can see right away the reaction of the acid with the copper in the leads of the ICs. You can see the green color that I was talking about that's going to be created. Now this is just a matter of now waiting game, because I'm going to slowly add acid to this as necessary, and of course change the amount of heat. I have a thermometer here to make sure that it doesn't get too hot, and I'm going to continue running this, and it's going to be a fairly boring reaction because once the copper is consumed, the reaction with the epoxy is pretty mild. So we can go ahead and continue doing this, and I'll keep recording bits and pieces of it as we go along. Alright, now the reaction is really underway. I've put a cover on top of it in order to isolate the acid from the oxygen in the environment, and also from the just generally contaminating it anymore, because the fumes are going to continue coming off as the surface of the acid is hot in this contact with the air. So we're going to continue going forward, and every occasionally I'm going to stir it with this Teflon tweezer and see what happens. Alright, so a whole bunch of time has passed by now. Let's get rid of this. Oh, that's just nasty. Here we go. It's, again, it's exactly the importance of doing this outside. So now I have you can see all the remaining portions of the packages. I don't think they're actually fully, you can see this one is still fairly intact, but they have certainly taken a big hit, so I think we're gonna have to run this one other time. I don't think the acid is very effective anymore. By the way, this is a heat plate that I was going to discard, that's why I didn't care for this to happen. So let's go ahead and dilute this acid a little bit. So here I have some ice water. Again, remember that you should always add acid to cold water, not the other way around. You should never add water to the acid. The reaction is quite endothermic. So exothermic, sorry, I meant. I'm going to go ahead and dilute this and then do this one more time. Here we go. Get rid of that. You can see whatever's left over is pretty nasty. It's interesting that some of the packages have had much more reaction than the other one. In fact, I don't even see the third package in here anymore. So I'm gonna have to go and clean this up with some water and some acetone and see what's left over, if we can find the other dye, and then go from there and do the same thing one more time to get rid of the remaining leftover of the packages. Well, and here's the result of the first round. You can see the first one, I can see the back of the silicon on that one. That's interesting, but it's very unusual that they reacted so differently. I presume that the reason for that is because they probably were not made of exactly the same type of epoxy. That's the only thing I can think of that might be causing this, but you can see this one has had quite a bit of its material already consumed by the acid. So what I'm going to do next is clean this up, like I said, dry them off because you don't want to have any water on them, and then repeat this process one more time with the acid again, and this time it should be much more effective because most of the metal is gone. So as a result, the acid will not react with the copper, and we will have a stronger concentration of the nitric acid remaining. So this is going to be a boring process of cleaning this stuff again and trying it one more time. So let's go ahead and do this, and I'll be right back. So here's some interesting, you can see that the package has been slowly eaten away, and all we have is now, you can see the bond wires just above the surface, and of course by doing this you're ruining the bond wires. The bond wires are, of course, they're going to get absorbed into the acid. as well. They're gonna react with it. So it looks like this one has become much thinner, this package, compared to the other one for some reason. You can see that it hasn't been dissolved away nearly as much, and this is the silicon, and on this side of it you can still see some of the bond wire. So this has to still go through some more of the reaction with the acid. So here we go. We're gonna do this one more time, round 2, and heat it up once again to the same temperature. Make sure I monitor it carefully, cover it up, and it's much better to do this twice than to put too much acid and have it spill over and have a big mess, and I'll have too much fumes, where the reaction gets out of control. Remember that once you heat it up, there's nothing really you can do. It's not like you're pouring water on it. Can be quite dangerous. So again, all the precautions in the world, is better to take a little extra time than to run into a major problem. All right, one more try. There we go. Hopefully that's good enough. And this time this is going to take us all the way. Let me clean this up just in case. Get rid of any questionable amount of water. Perfect. Now we wait again. So the reaction has started again. There's obviously some metal left still in this package, and that's reacting with the nitric acid. It's slowly heating up. Again, we don't want to heat it up too much, because once it starts boiling, then you're not really doing anything more at that point. So we continue to wait. Alright, looks like we are progressing nicely. Go some more of this nasty stuff escaping here. Yep, it looks like it's gone fairly good, and you can, stirring this thing out, you can see that more of the gas being released as it reacts with the air. You can see when I bring every time I bring the tweezers out, the hot acid reacts with the air really violently. Here we go, check it out. There are our dies, all 3 of them. 2 of them are facing up, 1 of them is facing down. The 2 that are the same size, I think are the microprocessors, but I'm not 100% sure. But interestingly, that actually not all the dies are the same size. I would have thought the 2 microprocessors would be exactly the same. But anyhow, I'm gonna have to go clean this up pretty carefully, and I also clean my hot plate and all that mess. Get some acetone, get these things nice and clean, and then we'll put them under the microscope. Alright, everything back to normal. You can see I cleaned everything, so there's just some discoloration on the heat plate, but everything's taken care of, and there's some discoloration here too, where the acid was touching my little thermometer. But everything is nice and good, so this can be of course used in the future, so there was no sacrifice at all. And here are dyes sitting in some acetone. And by the way, don't take pure acetone very lightly neither. It's extremely flammable, has a very low vapor point, so it can be quite dangerous. Just be careful. It's much more concentrated, of course, than what you find in nail polish remover. Alright, so it looks good. I'll just do a bit more cleaning. I think I'm gonna probably need to get myself an ultrasonic bath. That's one thing I don't have here in the lab. But anyhow, I'll just agitate this a bit, get all the debris off, get all the anything that's on there off, and then we can put it under the microscope. By the way, if you're curious, you can actually buy heat plates which are ceramic coated for this very reason. The ceramic coat protects against a really wide variety of chemicals damaging the plate. So this is not one of those models, but you could potentially get one that has ceramic coated on it, which is much nicer than the one that I have. Alright, I've placed the dyes under my microscope here, and you cannot see them because of the fact that the light from the microscope saturates the sensor of the camera, but they're all right next to each other. And I'm looking at them here on the computer, so we can now go ahead and do some very basic analysis of what it is that we are looking at. So here right now in the center of the screen is going to be the vacuum fluorescent display IC. Now I can go ahead and zoom in a little bit so that we can get a better look at it. Go ahead and get this guy back in focus. Now what do we expect to find? Well, the vacuum fluorescent display has some high voltage I/O drivers on it, and those are the drivers that will drive the different plates inside the vacuum fluorescent display, and these have to handle the larger voltages. And of course, as you know, in a VFD you have the 2 plates have to be at a large potential differences so that they can attract the electrons, and then the electrons will strike the surface of the phosphorus and then of course emit light. So around here in the corner you can see the pads where the wire bond would normally be connected to. All the wire bonds have gone away, and the wire bonds will be connected to these. I had to take some of the wire bonds off because the ones that are made of gold, of course, will not dissolve in the acid. So the ones that are all around here are all completely taken off, and you can see the pads where they used to be. Now you can see the large feature size here on the I/O lines and all around the IC, and of course this large feature size mean that there's going to be much higher dielectric breakdown of these devices. These are high breakdown devices used for the I/Os of the VFD driver. All the surrounding circuitry is basically I/O handling circuitry. In the center you can see much smaller feature sizes, and this is a section of the VFD driver that handles the serial interface. So you basically latch in a whole bunch of serial data into the shift register, and there's a state machine inside which then goes through all the states, driving individual pins rapidly and creating a steady picture across multiple digits of the VFD driver. And if you recall from the original video, there was a short between the high voltage VFD driver power supply and the 5-volt I/O power supply. And that is right over here. If you pay close attention, you can see that there has been a bridge, a gap between these two, creating a short circuit. And that short circuit that, of course, then has gone ahead and damaged all of the other circuits that were on the display driver. Everything else looks pretty good. There seems to be some minor damage here as well. But this, I believe, is the main point of failure. This failure cascaded into all the other failures that we saw on the display driver, breaking everything that was on the 5-volt rail because they got shorted to the 32-volt rail. And this is basically a major problem. And I'm very surprised to see how close these are on the die, but I'm not sure exactly what the designers were thinking when they went ahead and laid this out. But yeah, this appears to be the main point of failure. And here's a closer look at it, where you can see the bridge that has been made. Unfortunately, this microscope isn't intended for looking at such small details, so the image quality isn't going to be great. And a real optical microscope would be pretty nice to look at these features. I look at, of course, ICs all the time under the microscope, but this one doesn't show up very well here. But nonetheless, you can see a pretty good look at the larger feature size again of the output drivers, which are much bigger than the feature size of the components in the center. Overall, you know, it's a nice VFD driver, I suppose. And I don't know what the regular lifetime of these components are, but this one obviously broke everything. The next thing to look at are the microprocessors. Now this is interesting because based on the different sizes of the dies together, I can say with confidence that these two are not even in the same CMOS technology node. This is a newer technology node than this one. I'm not sure what the original technology node would have been for this processor, but you can clearly see similarities between them. You can see large blocks of memory present in both. You can see more memory here. You can see that split into two in this section. You can see half of it is here, the other half here. In this one, the two halves are broken up. There is also some more what appears to be either interconnect or some more memory here, which shows up there. Now the mask ROM in this is most likely all within here. Now we cannot see the individual bits in the mask ROM because, again, the microscope doesn't have enough resolution for me to zoom in, enough resolving power for me to zoom in and see it. Now I believe this microprocessor is the one that used to be on the original display. This discoloration that you see here is actually not from the IC. This is on the surface of the IC. This is a remaining of the package that wasn't fully dissolved by the acid. So this is not damage. The damage here appears to be in this section and in this section, and again, it makes sense that the damage would be confined to near the edges of the IC where the power supply was connected, and that has destroyed whatever that was here near the pads, because this IC, which was rated for 5 volts, had received 36 volts from the short from the VFD display itself, and has caused some major damage in here. You can see most likely this region here has been the biggest victim. But if you didn't know what the software that was inside the mask ROM microprocessor is, there are actually ways to reverse engineer it. You'd have to take a very high optically clear image of this section, and then you can see the metallization connecting various bits to either 1 or 0 of the program that runs on the microprocessor, and that will then can be translated into and be basically reverse compiled into some code which would be the code that runs on the microprocessor itself. People actually have done that, which is a lot of work and quite impressive, because once you have all the bits, you don't know where the start of the program is, and you'd have to run some correlation between where you think the start of the execution code would be, and then find out from that what the assembly code was, and so on. And people have done that. I think that would be in this region where the ones and zeros can be reverse engineered. But other than that, the rest of it, makes sense. This is what a typical microprocessor would look like. It would have sections of massively repetitive sections of memory and so on, and of course a whole bunch of other logic units there. But it's interesting to see the one that I bought is completely different from the one that was actually directly on the board. So that's of course why it didn't work. Other than that, it looks pretty amazing, and it's pretty nice to see that you can go ahead and decap an IC in a fairly straightforward, fairly simple way, and be able to get all this detail out of it. And if I had a nice optical microscope, then we could see even more details. I'll keep these. Perhaps in the future I might come across a microscope where I can do that. Well, that I think would be enough for this video. We saw, of course, the repair of the original one that I couldn't finish. So thanks, Gerry, for saying that IC in that would have looked like this, and now the unit is up and running, and of course the repair of the other power supply. So if you like it, please give us a thumbs up. It always helps in the ranking, and of course leave a comment, let me know what you think, and if you have any other background information on these, of course share it with the other users. So until next time.